All right, guys, welcome back. I wanted to make this video, and it's going to be a little different than what we've done in the past. Typically, we cover whole sections in videos, but here I just kind of wanted to cover one problem. And it's a problem that most of you have already seen. Most of you saw it at the end of class on Tuesday, introducing section 8.8, which is all about exponential growth and decay. And this one's all about the population in Florida. And while we were going through it, and some of you got the right answer, I think you got pretty confused by some of the work I did on the board, or maybe you're someone who's quarantining, you didn't get a chance to see it. So I wanted to take this chance to show this video, or rather make the video, so that you could see the process involved in this problem and how it leads us into exponential growth and decay. Again, I wanted to do this so you could watch it through, have a chance to pause it. I'll talk about it a little bit in class on Thursday, but I'll probably reference this, so hopefully it provides some insight. So here's the problem we're dealing with. In 1990, Florida's population was about 13 million people. Since 1990, the state's population has grown about 1.7% each year. We want to know, what's the population in 1991, 1992, and what about a year like 2008? Now, if you haven't had a chance to solve this yet, if you're someone quarantining, go ahead and try this problem. See what you can come up with. Okay, hopefully if you're a quarantining person, you pause the video. Maybe if you've even already done this, you reference this, you look back in your notes and you see what you did. And I'm going to focus first on 1991, then we'll move to 1992, and then 2008. So let's first talk about 1991. Now, most of you in class, and I'm willing to bet if you were at home, did something along these lines. You said, okay, the population is 13 million people. 13 million. Well, we want to take a percentage of that. Okay, we're growing by 1.7%, but in order to grow by 1.7%, I have to know what is 1.7% of 13 million. What I hope you did is in turn, you then said, well, I'm going to multiply by 0.017. If you're someone who multiplied by 1.7, pause the video, erase the 1.7 and put 0.017. Why? Because the decimal point moves to places when we go to percentages. Think about it like this. 100% is the same thing as 1, which means 1.7% is going to be the same thing as 0.017. Okay, 25% is 0.25. You get the idea. So what I hope you did is you multiplied that, and when you did that, you got 221,000. Now, this wasn't your final answer because that wouldn't make sense. We're growing by 1.7% each year. If the population went from 13 million all the way down to 221,000, that's not growth. So hopefully the last step you did is you said, well, 1.7% of 13 million is 221,000. So I am going to add that 1.7% to the 13 million that I started with. Why? Because I'm growing by 1.7%. I started at 13 million. 1.7% of that's 221,000. So if I'm growing by 221,000, 1.7%, I am ending up with a total population in 1991 of 13,221,000. Okay? Essentially, it boils down to you multiplied, if I were to rewrite this, what you did is you took your original value, multiplied it by the percentage, and added it to the original value. And that's how we got our answer. Now, that's for 1991. What will we do for 1992? Well, if you got the wrong answer for 1991, go ahead and pause this and see if you can figure out the answer for 1992. Again, if you're someone who's already done this part, hang with me here. What you then do for 1992 is you apply the same logic. If I want to figure, if the population's growing by 1.7% each year, then whatever my population was in 1991, I need 1.7% more in 1992. Well, my population in 1991 was 13,221,000. Since we're growing by a percent, we can't just keep 13 million here. That's applying the 1.7% increase to 13 million, since we're growing by that amount each year, gets us from 1990 to 1991. But to get from 1991 to 1992, I have to grow the 1991 population by 1.7%, which means I got to grow that 13,221,000 by 1.7%. Again, what I'm going to do is I'm going to figure out what 1.7% of 13,221,000 is, and I'm going to add it to my starting population from 1991. When you do this, you get 13,445,757. What I hope you see is the process we use for finding the population. I think you could probably at this point find for me the population in 1993. Because you would tell me, well, you're going to take your value from 1992. We're growing by 1.7% each year. So take that 1992 value, find out what 1.7% of it is, add it to your original from 1992. Again, we can't add from 1990 the 13 million, right? That would not be accurate. So here's where it gets tricky, because I asked you what's the population in 2008. Well, we've kind of got the process down, but man, that's going to take a lot of work. Going all the way from 1991 to 2008, I'm going to have to do this, or 1990 to 2008, I'm going to have to do this 18 times. It's quite a bit. So could there be an easier way to do it? Answer, absolutely. Let me show you how. The way we can make this a little simpler is by doing some rewriting. Let's re-look at 1991. Since most of you did what's in green, and I love that, I want to simplify it. Well, how could I simplify it? I can simplify it by really simplifying what we did here. You're taking your original amount, multiplying the percent, and adding the original. Well, we learned back in middle school, if I had something like, I don't know, 2 times 3 plus 2, you could identify what's called the greatest common factor. What's the greatest common factor shared between these numbers? Well, 2. Consequently, that means we could take the 2 out front and rewrite what we had. If you don't believe me, check the work here. 2 times 3 is 6. 6 plus 2 is 8. Consequently, if we write it like this, 3 plus 1 is 4, times 2 is also 8. We're taking the greatest common factor out. If you want another example, what if I had 4 times 3 plus, I don't know, 16? Well, what's the greatest common factor? Well, both the 4 and the 16 are divisible by 4, leaving me with 3 plus 4. Again, if you check your work here, 7 times 4 is 28. 4 times 3 is 12, plus 16 is 28. Again, identifying the greatest common factor in a set of numbers means we can take that number out front. It's a different way of writing it, so to speak. Should have learned that in middle school. If you haven't, as always, shoot me an email. Let me know how I can help. So I'm going to rewrite what we learned in 1991 by identifying a greatest common factor. When I look at the left side, what do I notice? Each term has in common? They both have a 13 million. So what I'm going to do is I'm going to take that 13 million out front. What's that leave me with? 0.017 plus 1. Where's the 1 come from? Well, if I take the 13 million out, and I would do it, in other words, I would divide the 13 million times 0.017 by 13 million. And I would divide 13 million by 13 million. I just get 0.017 and 1. Again, that would come from the idea that taking something out front means you're dividing both terms by it. So what's happening here? Well, I've just rewritten it. Again, the answer isn't going to change. If you don't believe me, go ahead and distribute, and you'll figure out that your answer is still 13,221,000. How could I rewrite 1992? Well, 1992 could be rewritten as 13,221,000 times 0.017 plus 1. Again, that will give us our answer that we got before, 13,445,757. Okay? Again, folks, it seems a little long-winded, but all I'm doing here is I'm taking what you did in green and rewriting it. Now, what happens is I can do one more rewriting here, and it's going to help illustrate my point. 13,221,000 we learned is equal to 13 million times 0.017 plus 1. So what I could do, we learned about this in chapter 7. What I could do is I can substitute 13 million times 0.017 plus 1 in for that 13,221,000. Now again, if you're like, why in the world are you doing this? Just hang with me. I promise it'll make sense in a second. Again, this concept is based on substitution. So I'm substituting the 13,000,017 plus 1 in for the 13,221,000. And then again, I still have this 0.017 plus 1. But what I notice now is I have a 0.017 plus 1 written twice, and we've been learning all of chapter 8. If you have something multiplied by itself, rewrite it as an exponent. Just like that. Again, if you don't believe me, if you would apply the exponent and then do distributing, you will get your answer of 13,445,757. So why am I doing this? Here's the point. Let me summarize what we've done so far. In 1990, and this is the part I really want you to hang on to, our population was 13 million. In 1991, our population could be found using this setup. It's the same setup you all had, I just edited it a bit. In the middle, we got the formula. At the end, we got the answer. In 1992, our setup was 13 million times 0.017 squared, or plus 1 squared, and that gave us our value. Now at this point, pause the video and see what you notice. What I hope you recognize, hopefully you're not too royally confused about the process we've gone through, is the only thing that's changing every single time is this exponent. You might be going, what the heck, there's only one exponent. Well, think about it. 0.017 plus 1, when I don't write an exponent, we've learned that if no exponent is written, there's a 1 there. What about this 13 million? Well, we could also write that as an exponent. To the 0 power. Why? Because anything to the 0 power is just 1. Well, if this is all just 1 times 13 million, then I'm just left with 13 million. What I hope you see is, folks, through this various steps of algebra, which, while admittedly is confusing, brings us to a great conclusion. Because I'm willing to bet, while you might be confused on some of the stuff we've done, if I asked you to find for me the population in 1994, your setup would be this. And you get your answer. In a much simpler time than writing out all 18 versions of original plus percent, or times percent plus original times percent plus original. What about our original question? Of 2008? Well, since 1990, that would be 18 years. And I would just simply plug this in and solve. Folks, here's the point if you get nothing else. When we are working with growing or decreasing by some percent, we have the option of starting out and logicking through it like you all probably did in green. I take my original amount, I multiply it by the percent, and I add the original. But the problem with that is, what if we want to look a significant amount of time in advance? If I want to know 5 years from now what the population is, and we've been increasing every 6 months by a certain percent, that's going to take a lot of work by hand. But through some different algebra steps, we can see that we have a little formula we could use that makes life a lot simpler. What could we deduce from this formula? Well, think about what our values were. 13 million was my initial amount. In parentheses, I'm taking my percent plus 1 because I'm growing. You can probably bet in your head, what would you do if you were decreasing by a certain percent? Let me rewrite this like this. If we were decreasing by a certain percent, this plus sign would just become a minus. And what was our value in the exponent? Well, it was how much time had gone by. Well, we learned in 8.7 our initial amount was A. The middle area, we called this guy B, and X was our change over time. Folks, I'm going to end the video there. Hopefully your interest is somewhat piqued. Again, if you are super confused at any point, don't worry about it. We're going to do a lot of examples to go through it. Put some stars there of what's confusing to you, and I will happily help you with it. But this is what we're going to focus on. The point of this problem is not, I really, really care about how many people are in Florida in 2008. The point is, we can find easier ways to figure out what populations or certain values are when they're increasing and decreasing by a certain percent. Guys, hopefully this helps clarify stuff. Thanks for watching. Have a great day.